We have learned a lot of rules about the first derivative, but in the application we may need sometimes the higher derivatives of the given functions. As we have seen today about the concavity or the extremum points, you might need to use the second derivative or sometimes even higher derivatives. If the second derivative or the higher derivative applies, and if they exist, we can apply the similar rules what we have learned for the first derivative as well. So you can just go ahead after taking the first derivative, you need to take the second derivative as you are taking the first derivative, guys. So all the rules will stay same as long as, okay, your higher derivatives exist. What we mean by that, if you show that already by using the limit definition, you don't need to, but the existence means, okay, that limit should exist, okay? So, and then you can go ahead and then apply the same rules as we apply to the first derivative. We will be using, okay, different notation for the higher derivatives. So still you can use the prime notation, and then as well as look at that this other Leibniz notation, and then this is another notation you might not need for this class, but for some other class, okay, those notations needs to be used. So now I'm going to give you a couple of examples about how we are going to take the derivative, higher derivatives. Then we are going to start using the higher derivatives to learn more about the concavity and then extremum points. Let's take a look at this example and then try to see the difference between the first, second, and then third derivative. If I like to, okay, take the first derivative, as this is the polynomial, that's why I'm going to be using just the power rule. So the first derivative is going to be equal to 20x cubed minus 6x plus 3. And then I'm going to continue, look at that. I'm taking the derivative of the first derivative. I'm just applying the power rule, which is going to be equal 60x squared minus 6, right? So I can continue to take the third derivatives, look at that. This time I'm going to take the derivative of the second derivative, right, which is equal to third derivative. So which is going to be equal 120x. The derivative of the 6 is going to be equal to 0. You want to continue? Yes, we can continue. The fourth derivative is going to be equal, look at the derivative of the third derivative, which is going to be equal to 120. And then the last derivative I can take for this polynomial would be the fifth derivative, which is the derivative of the constant in the fourth derivative, which is 0. Then you can continue, but all other derivatives will be 0, right? You don't need to continue that. And you can just say that all other derivatives after the fifth derivative is going to be 0. That is how I take the higher derivative, as you see. So you can just use all the rules you have learned about the first derivative, but you need to apply the derivative, to the previous derivative to take the next derivative. One more example, let's look at the product rule, how it could behave under the higher derivatives. I'm just going to take the first derivative. First derivative is going to be about the product rule. First I need to take the first function derivative, which is going to be equal to 3 times e to the 3x times, I'm going to keep the second function same. And then I'm going to keep the first function same. I'm going to take the second function derivative. As you see, first function, the first derivative has now the two terms, we just started one term, but now after product rule I apply, I'm going to have the two terms. If I apply one more derivative, as you can predict, I'm going to have the four terms. But look at that now, what I did in the first derivative, I applied the chain rule, as well as the exponential derivative, as well as the power rule, and also I applied the product rule. Look at that, I'm combining all the rules I have learned in one question. Now, the second derivative, I'm going to take the derivative of the first term, which is going to be equal to 9e to the 3x, keep the second one same, and then take the second derivative, 2x, second function derivative, and then keep the first one same. Now I'm done with this one. So look at, now I have the other one here, which is going to be equal, take the derivative of the e to the 3x exponential function, keep the second one same, and plus, look at that, e to the 3x, keep same, and then the derivative of 2x, which is going to be 2. Of course, you can arrange all these terms, okay, since you have a lot of same type of, look at that common terms here, you can combine this one, 12x e to the 3x, and plus 2 times e to the 3x, and then plus what I have as a first term, 9x squared e to the 3x. As you see, if you try to take the third derivative, it's going to be more messy right around. So it is not a good thing, okay, to apply the higher derivatives unless you don't need it. It's time to talk about concavity. As you see from the graph, right, we have two situations here. The concave upward type of, right, the region of this graph, and then concave downward region of this graph. As you see, if I have the heel right here, you can definitely say, right, the function is concave downward here. But if you have the volley here, okay, your function is going to be concave upward. There is another way of saying this one. If you have look at that, your curve is under, right, the slope line, okay, you have definitely concave downward. But if your curve is right above the slope line, okay, you can definitely say you have the concave upward graph. So, but these are just the general, the heuristic definition. We would like to give the definition related with the derivative, guys. So now I'm gonna do a couple of observations about the derivatives, and then we will see that there is really a relationship between the derivatives of the function, even the higher derivatives, with the concaveness. Look at this red line. These red lines are the slope lines. In other words, those are the tangent line, as well as those are the derivatives, as you know. So what happens here, as my function increasing, right? As you know, if my function is increasing, yes, of course, my derivative is positive, and but also my derivative, this slope line slope, right, is my derivative is decreasing, as you see, right? This slope line slope, the tangent line slope get decreasing, as you see, when I write the when I move on this curve, as you see. So what does that mean? If my first derivative decreasing, right, that means, right, what can you say about its derivative? If you remember from the first section, if my function was decreasing, but my derivative was, right, less than 0. So can I use, right, the same logic for my first derivative? Now this is my function is here, right, the derivative, first derivative. If my first derivative function decreasing, what you can say about is second derivative. Second derivative is going to be less than 0, right? So I can say the similar thing, look at that, about, right, this part, concave upward, look at that, I have my derivatives, my tangent line, but if you look at my tangent line is increasing, right? The slope of my tangent line is increasing. That means my first derivative is increasing on that part. That means my derivative of derivative is going to be positive, right? The second derivative is going to be positive. So now look at the graph again, and then try to create this relationship. If you have the concave downward, right, that's the right observation with it. But if you have the concave upward, that's the relationship, right, that we observed. So we can definitely summarize, right, this in this definition. So if you have, right, the second derivative less than 0, then you can say that you have the concave downward, right, concave downward. When you have, right, the second derivative is less than 0, concave downward. But if you have, right, the second derivative is bigger than 0, then you can say that you have the concave upward graph in that region. Okay, so around that x, we are working that. Okay, that's the concavity, but now we are going to be using the concavity for further job. We are going to try to relate the concavity with the extremum points. But let's look at, okay, how we can figure out the concavity of a given function. Before starting the example, you need to consider this point as well, which we will call the inflection point. As you see, right, these are the points. Your function second derivative, right, will pass from negative to positive. If you have such a point, right, that's going to be called the inflection point. And when you pass this, right, your inflection point, your second derivative will be 0. But there is no guarantee for any function, right? If you have the second derivative, 0, we cannot call that point, okay, is the inflection point. The reason is that you need to have, right, this passing, right, from negative to positive. But those are the points which your second derivative is 0, okay, are the, right, some points you need to consider if they are the inflection points. So let's look at the examples now. Let's look at this example. As you see, I don't have any graph, but I'd like to learn, okay, the concavity by taking this second derivative. So the first derivative of the logarithmic function, as you know, right, you need to take the derivative of the inside to the x, or, right, whatever you have inside, you need to put that one to the bottom part. Okay, second derivative is going to be equal then 2 times, right, the bottom part, and then the derivative of the bottom part times, right, the top part, and then you need to take the square of the bottom part. Okay, let me arrange the terms I have there. 4x squared, which is going to be equal negative 2x squared plus 1 I have, and then x squared plus 1 squared. Okay, now I need to check out, right, when this expression is going to be less than or bigger than 0. As you see, the bottom part is always bigger than 0, right? Since we have the square, this is always bigger than 0. That's why, okay, you need to check it out when this expression is going to be bigger than or less than 0. So let me try to see, okay, when it is going to be less than or bigger than 0. Negative 2x squared plus 1, I need to have, right, I need to have this expression is bigger than 0. So if I solve this inequality, if you remember the reference section, right, so 1 should be bigger than 2x squared, and then, but as we have noticed, guys, I think there is a small mistake here with it. That should be the 2, not the 1, coming from the, right, the multiplication here. If you multiply this, that should be 2. So let's go ahead and then fix that issue. It's gonna be easier. And look at that, this is also 2. So now 1 should be bigger than x squared. When x squared should be less than 1, when, right, the x is between negative 1 and 1. Okay, if you keep the x, right, between these, so what will happen? Your second derivative, right, will be bigger than 0. That means your function, right, which is ln x squared plus 1 will be concave, right, up. And but if you have the, right, the value which is not between these, which if you have, right, value which is bigger than 1 or which is less than negative 1, then your second derivative is going to be less than 0, and then you can just say that your function is going to be concave down. But when you have these values, right, they are equal 0, your function, right, is going to be equal 0, and then as you see, my function second derivative is also passing from positive to negative. That's why you are going to say at x equal 1 and then x equal negative 1, I have inflection points. As you see, without seeing the graph, right, I'm able to say where I'm going to have the concavity upward or the downward using the second derivative test for the, right, the concavity. I just use the second derivative to be able to say about the concavity. Finally, it is time to talk about the concavity and the relative extremum relationship, guys. Finally, it is time to talk about the concavity and the relative extremum relationship, guys. As you see, right, from this graph we just used before, right, when you look at the concave downward or the concave upward shapes on different region, we have also, right, the minimum and the maximum point. So as this graph suggests, right, we can definitely create a relationship between the second derivative and then as well as the extremum points. As you see, if I have the concave downward, yeah, I had, right, the maximum point, and then I had the, right, the minimum point when I had the concave upward type of graph. So, but we need to add right these observation to our right the theorem, which we will call the second derivative test. Look at what it says. If you have a critical point, right? As so, if you have right your function derivative which is equal 0, that was right one of the critical points definition. If you have this critical point, and then if you satisfy right your second derivative is bigger than 0, you have the relative minimum. I know from right the second derivative test we just saw right we just created the relationship between the second derivative and the concavity. So I'm using that one. If I have the second derivative which is bigger than 0, I know that I have right the concave upward type of right graph. So if I combine this one right by the critical points, I'm just gonna have the relative minimum. And if I do the other way around, look at here. If I have the second derivative which is less than 0, and then also I have the right the critical points, that's how I'm gonna have the relative maximum. But if you have the right the second derivative and then as well as the first derivative 0 at that point, so this test will not work, okay? You just need to go back and then you need to use the first derivative test, right, to figure out if you have the maximum or the minimum points in your function. So second derivative test is going to be more useful sometimes, okay? If you don't want to use the first derivative test, okay, this is easier, simpler, since you are just checking, right, you are not checking the interval, you are just checking, right, if you have the 0, right, the critical points, as well as if you have, right, the second derivative sign positive or the negative to give the right the relative minimum and maximum. So I'm going to apply this idea right to some problems, and I'm going to show it to you how you can use the right second derivative to figure out if you have the if you can find the minimum and the maximum point. Look at this function. My question is about finding the extremum points, guys. This is why first I need to take the first derivative to figure out the critical points. The first one derivative is equal negative 2x minus 10. So I need to make it equal 0. And then x is going to be equal negative 5. As you see, this is my critical point. And then it makes my first derivative 0. What I should do, I should be checking out, right, the second derivative at this point. As you see, second derivative is equal what? Just negative 2. So, which is less than 0. If it is less than 0, what will happen? You will have the concave downward of the graph, right? Since the second derivative is less than 0, concave downward. That means, right, at x equal negative 5, you have, right, the f has a relative extremum, right, the relative maximum point, guys. That is how I'm gonna determine if I have the relative maximum or the minimum. As you see, it is so easy, easier than the first derivative test. So step 1, check it out. Okay, what is your critical point? Step 2, right? Check it out if your second derivative is positive or negative. Based on that information, you can decide if you have the relative maximum or the minimum points. So now it is time to look at some real world examples using the second. So look at this drug concentration example. The percent of concentration of some drugs, okay, in your blood was given by this model, guys, okay. After 3 hours, you can have this concentration of that type of graph in your blood could be given by this model. So what I would like to find out when it is going to be this concentration is maximum. That's why you need to apply either the first derivative test or the second derivative test to figure out the relative extremum points. That's what I do here. Since this is the rational function, that's why when I take the derivative, I need to apply the quotient rule. As you see, take the derivative of the first one, which is 3, and then put our second one, and then put the first one, okay, without modifying it, and then take the second function derivative on the bottom, and then take the square of the bottom part. So that's the quotient rule I just applied, and then this will give you some critical points. These are my critical points, since those are the points which makes my derivative 0. But look at that, since this function is always positive, and then the domain of k is positive number, since time cannot be negative. That's why I can use this one. So my only critical number is going to be 2. So what I should do, I should be checking out the second derivative if it is positive or negative. Take the second derivative using the quotient rule again. If you take the quotient, if you apply the quotient rule, you will find out your second derivative in this way, and then at t is equal to, after 2 hours, if you put that one right into second derivative, you will find out right that this number, which is less than 0. That means right you have the maximum point right after 2 hours. So the concentration will be maximum after 2 hours. What is going to be the concentration amount? Of course, you need to really put that number, that value into your function so that you can figure out what's going to be the concentration amount, guys. The other example comes from the breast cancer research. So breast cancer tumors, okay, grows by this equation. They modeled, okay, by this one. This is the time, and then there's the number of the growth, or the number of cancer cells after T days. So C and then K numbers, okay, is given by these constants. So they want us to find out the inflection points. What was the inflection points? First, we need to figure out when your second derivative is 0, but this is not guaranteed, right? You need to find out when your second derivative, right, will change its sign, right? The positive, negative. First, I need to take the first derivative. You need to be careful since this is a hard example, since it includes, right, the chain rule, since you have, right, the composition of functions. So exponential function derivative, right, will be just first you need to, right, put it down as it is, and then you need to take the derivative of what you have right on the top. That is what you see here, right? As you see, you are just going to take the derivative. When you take the derivative, still you have, right, another exponential function. C times one derivative, which is going to be 0. But the C times this one, right, you just need to put that one down without changing, as you did here, and then take the derivative of the top part, right, the derivative of this one. So let me take the derivative, which is going to be equal to negative k, and then another negative here, which is going to be positive, and then you need to keep the rest same, right? That's the first derivative will complete. And then second derivative, okay, you need to take a second derivative using the same idea, follow the same rules. So then look at that. This is my second derivative. I need to figure out when this second derivative is going to be 0. If you solve this equation, right, the t will be this one. So your second derivative will be 0 at those points. Okay, great. And then I know what the c and then k were, right? They were given in the question. If I use those constant, my t is gonna be equal almost right to 301. So now this guy could be an inflection point. What I should do, I'm gonna have right there some value less than 301 and then bigger value which is bigger than 301. I'm gonna check them out, right, if my second derivative is positive or negative. As you see, right, let's take the 200. If I use the 200 in second derivative, as you see, that's gonna give me, right, bigger than 0. So I can definitely say, right, if my second derivative is bigger than 0, I have, right, the concave downward type of shape. And then if I am checking, right, to look at that and second derivative 400, that's gonna give me, right, the less than 0. What happens, as you see around, right, this point, which I was trying to figure out if it is inflection point, my second derivative changed its sign. That's why, right, I can definitely say it's going to be inflection point, since n is the function number of tumor cell function, is going to be positive in this interval, and then it's going to be negative on this interval. But at that point, right, it's going to be 0. So it is definitely the inflection point. What does that mean, right? What type of information I can derive from the inflection point? Look at it. It says rate of growth begins to slow down, right? Since I know that the inflection point is going to be something like that. As you see, right, there from concave upward to concave downward. So this is the inflection point. As you see, it starts decreasing, right? So the rate of change, here, right, the number of cancer cells growth the rate of number of cancer cell growth will decrease. That is what I can derive that. But so depending on what type of the drug you use, that might be this, that might be this, so that you need to model that part, so that maybe you can decrease this change by applying the different treatments, since those treatments will change the dysfunction as well, since depending on what treatment you apply, the number of the cancer cell model will change, and then depending on that part, look at it, I can observe that, these type of things, so that I can decide what treatment could be applied to my patients.